This video shows the working model and simulation of complex floating point addition. So the complex numbers are taken A R and B R and with the real parts, and AI and BI being the imaginary parts. So this is the top module of the complex floating point addition. So the complex addition is simple, that is the real parts are added separately and the imaginary parts are added separately. However, the addition here is a floating point addition. So basically a floating point number representation has three parts. One is sine, the second is exponent, and the third is mantissa. The number of bits required for each part depends on the precision requirement. Here we have considered single precision floating point number representation. So we have 1 bit for sine, 8 bits for exponent, and 23 bits for mantissa. So float add is the module which does the floating point addition. The floating point addition again has the inputs A and B, which are of 32 bits, and AZ and BZ are the hidden bits of the mantissa. The three steps that are required for the floating point addition are: the first thing is the exponent normalization or the exponent equalization. The second step is the mantissa shifting, and the third step is the mantissa addition. So C is the output and CZ is the output hidden bit of the mantissa. So again here recurse sign is a integer addition module which is required for the mantissa addition. So this integer addition module has three inputs. One is P, Q, which are the actual addend and augend, and mode is the one which decides whether the P and Q should be added or subtracted. And the num parameter defines how many bits of adder are required. So if you change the parameter num, this particular module recurse sign works as like let's say 25 bit adder over here. If I change it to 10, it works as a 10 bit adder. So now for this integer adder, we have again three modules. One is single bit adder, and then we have KGP generation, which is kill, propagate, and generate part, and then we have recursive stage, which is the implementation of parallel prefix tree. So now let us look into the test bench of the complex floating point adder. So this is the test bench, and I have included all the required submodules for the complex floating point adder. And yes, M is a mantissa parameter, N is an exponent parameter. I have instantiated the top module over here. And now coming to the inputs. So this part is the inputs for all the real part of the complex number, and these are the inputs for the imaginary part of the complex number. I have taken inputs in this way, where I have divided the entire 32 bits into parts. So these two are the sine bits, these are the exponent bits, and these are the mantissa bits. So these are the inputs I have taken. I have just commented it for the reference. And again, after some delay of 10, I am changing the imaginary part of the inputs and leaving the real part as it is. So I do have this inputs at time 0, and I do have this input at time 10. So next the step is to dump our value change dump file and then monitor the outputs. And now let us simulate this complex floating point adder and check the correctness of the output. So for the simulation, we are using iCarus Verilog, and the command required for this is iVerilog. -G 2001 is for the specification of the version, and since I have included all the required submodules over here, I need not specifically write down the submodules over here, so I'll just call the test bench alone. So to view the output, we have bvp a.out, and yes, Here I have separate sign bits of both inputs and separate exponent bits of both inputs and separate mantissa bits of both inputs, for which these are the separate sign, exponent and mantissa of the real parts, and then here comes the imaginary part. So now let's look this as a waveform. So yes, we are using a GTK wave tool for that. So now we need to call this value change dump file over here. So let us insert all the waves into the waveform viewer. Now AR, AI, AR, BI, BR are the inputs, and mode is for the addition, XI and XR are the outputs. So now let us look into the correctness of the output. So the first set of inputs that I have given were A is 0.5 plus I 0.5. So the A's real part was 0.5. This is 0.5, and B real part is this. So the output real part should be 0.9. So let us check whether this hexadecimal representation is equivalent to 0.9. So yes, this is equivalent to 0.9. Now coming to the imaginary part of the first set of inputs, it is 0.5 and this is 0.3, which should give us 0.8. Let us check the value. So this is 0.8. Now coming to the next set of inputs, I have not changed any real parts. So the real part output is the same. I've just changed the imaginary part. So the imaginary numbers were 1.2 and 1.5, which should give 2.7. So now let us check this value. Yeah, this is 2.7. So this is the working and the correctness of the complex floating point adder. Thank you.